Okay, I think we can start. Ashok, do you hear me? And you can start. I think you can start lecturing whenever
Okay.
you're ready.
Yeah, okay, thank you. Okay, so let me begin by recalling what we ended with yesterday. So we basically said that all correlation functions on the sphere okay, which is basically plane plus the point at infinity, are invariant under Slqc. Okay, so let me now write down the precise relation that it implies. So it basically says that if we have a correlation function, say, then this is equal to the transform of these by some Slqc transformation. So where H is an Slqc transformation, so H of Z is AZ plus B over CZ plus D. And you can put one condition in this, AD minus BC equal to 1. Okay. And these in general can be complicated if he is not a primary. If he is a primary, I gave you explicitly the transformation laws. Okay. But these are well-defined objects. Okay, whether it's a primary or secondary, these are well-defined objects. So this is a definite relationship between the between these two sides. Okay, that these should be equal. And so this H has 3 complex parameters. So this has 3 complex, or that is 6 real parameters. And this implies strong constraint on the correlation functions. In particular, using this, we can fix the dependence on 6 of the 2n variables z1 to zn. Okay, each z is a complex number, so there are 2n real variables, and basically this relation tells us that there are effectively 2n minus 6 independent variables. So let me now describe some consequences, specific consequences. These are easy to work out, but I'll not give the derivation. So first, if V1, V2, V3 are primaries of weight H1 bar, sorry. Then the following relation holds. So first of all, the one-point function equal to 0 unless H1 equal to 0, H1 bar equal to 0. Okay, of course, even in this case, it can still be 0, but this is a necessary condition for this to be non-zero. Two-point function this has the structure of some constant C12. Then you have to have H1 and H2 equal, H1 bar and H2 bar equal. And then we have a Z1 minus Z2 minus 2H1, Z1 bar minus Z2 bar. H1 bar. Okay, where C12 is some constant. And then you have a relation on the 3-point function. So this has a structure of a constant. And times anti-holomorphic pieces. The exact analog of this. All of these having bars on top. There is one more relation which is very useful. So let me write this, that suppose we have a operator, we have a correlation function of the following form. Where this is primary, of weight H1 bar, but these are not necessarily primary, can be anything. Then for large Z, this falls off as Z1 to the minus 2H1, Z1 bar to the power minus 2H1 bar, times some function of the rest of the coordinates. This, of course, assumes provided Z2 to Zn, none of these are at infinity. Okay, so these have to be finite points. And if these are finite points, sorry, this mistake here, this should have been Z1 bar. Okay. So if these are kept at finite points, and if you take the argument of this to infinity, okay, then it falls off as Z1 to the minus 2H1, Z1 bar to the minus 2H1 bar. Okay. So these are general relations in a CFT. In a CFT. So what we are going to do now is to apply it to the specific case that we have. We will apply it to our CFT. Okay, and see what kind of results we can get. So some consequences. So let's consider this correlation function. Now, if you recall, B has weight 0, 2, and this has weight 0, minus 1. So this is 0. Okay, because they have different conformal weights. So this is 0 by the identity on the 2-point function. But now if you take the Z goes to W limit, this becomes 1 over Z minus W times the expectation value of the I of 1. So this means that the expectation value of 1 is 0, okay, which means that the vacuum has 0 norm. Okay, so this is first consequence. Now let's consider this object, Pz C. So W here is just a new point. It's not the W coordinate system. Okay, maybe I should have, it doesn't matter. CZ1, CZ2. Okay. Now this we can analyze in different ways. Okay, but let's do it this way. So this is a correlation function. Okay, B is a primary of dimension 0, 2. So this means that as Z goes to infinity, this should go as Z to the minus 4 times some function of Z1, Z2. On the other hand, from the operator product expansion, we know that this one has poles at Z equal to Z1 and Z equal to Z2. Okay. And it's analytic function, okay, because it's a function of Z, okay, so it's a holomorphic or monomorphic, because del Z bar of this would be 0. So given this asymptotic fall off, okay, this implies, this is a simple exercise in complex analysis, okay, that the number of poles minus number of zeros in the Z plane is 4. And now you see that there is a contradiction, okay, because this operator product singularity tells us that it has poles at most at 2 positions, Z1 and Z2. Okay. Whereas this one is telling us that the number of poles minus number of zeros should be 4. Okay. So this is a contradiction. Okay. So this leads to contradiction. Okay. So this means it must vanish. Okay. And now you can take the Z goes to Z1 limit, pick up the residue, which means that the 1-point function of C is 0. Okay, I hope this is clear. We just, once we have shown that this vanishes, we can just go take Z towards Z1. We know that it should be 1 over Z minus Z1 times the expectation value of C of Z2. So that tells us the 1-point function of C must be 0. Similarly, if you consider this, also vanishes by the same argument. But it has at most 3 poles. 3 poles. And hence inconsistent with Z to the minus 4 fall off at infinity. The one that has a chance to be non-zero, okay, is the next one. Okay, and now let me also say that if we take the Z goes to Z1 limit, we'll tell us that a 2-point function of C must vanish. Okay. So the next one, this one can be non-zero. Okay. Since we have four poles. And now if you take Z goes to Z1 limit, this will mean that CZ2, CZ3, CZ4 can be non-zero. And then by the general form of the 3-point function, we know that this has to be proportional to Z1 minus Z2, Z2 minus Z3 times Z1 minus Z3. Okay. Now you can ask, what about the next one? If we take CZ1, CZ2, CZ3, CZ4, this in fact can also be shown to vanish. And the reason is that let's look at it as a function of Z1. So this one should go as Z1 squared, because this has conformal dimension -1. Okay, so this should go as Z1 squared as Z1 goes to infinity. So this means that the number of poles minus number of zeros is -2. Okay, there are more zeros than poles, okay, because it's growing. Now this one, because C is an anti-commuting operator, okay, this has to be antisymmetric under Z1 Z2 exchange when it comes close. Okay. And because it has no singularity, this means that this must vanish at Z1 equal to Z2. Okay. So this has zeros at Z1 equal to Z2 or Z3 or Z4. Okay, I'm looking at it as a function of Z1. Okay, of course, you can similarly look at it as a function of Z2, but let's just think of this as a function of Z1. So you see, they already have 3 zeros. And you cannot have any pole, right? Because there is no B here. Okay, that's the place where C becomes singular. Okay. So number of poles is 0. Okay. Number of zeros is already 3. Okay, at least 3. And so there is a contradiction again. Okay, so you cannot have -2. So this must vanish with contradiction. Okay, which implies that you cannot even have more series. Okay, now let's go back to the previous expression. CZ1, CZ2, CZ3. Okay. We say that this may be non-zero. At least we have not so far argued that this is 0. Okay. But it could be 0. Right? And in fact, we will now argue that this indeed is 0. Okay. And the way to argue this is that let's take this and then insert a pair of operators, B bar Z bar, C bar Z 1 prime bar. Okay. Now you see, now let's look at it as a function of Z bar. Okay. So this should go as Z bar to the -4 as Z bar goes to infinity. Okay. Which means in the Z bar plane, okay, number of zeros, number of poles minus number of zeros is 4. Okay. But as a function of Z bar, it has only 1 pole. Okay. But only 1 pole. But only 1 pole at Z bar equal to Z1 prime bar. Okay. So which again means that this must vanish. Okay. And now by picking up the residue at Z bar equal to Z1 prime bar, Z bar going to Z1 prime bar, this implies that CZ1, CZ2, CZ3 is non-zero. So in this class, the one that satisfies all the consistency conditions for being non-zero is the following. the non-vanishing correlation function is this one. You have to have 3 C's and 3 C bars. This can be non-zero, okay, and this is proportional to Z1 minus Z2 Okay, so this is the basic correlation function, and I'll leave it as an exercise to check, to prove that in any, okay, maybe I should define first, define ghost number. We'll assign ghost number 1 to C bar and -1 to B bar and 0 to matter, okay, which means anything that is constructed out of X. Then one can show that a correlation function can be non-zero only if the operators have ghost number 3 in the holomorphic sector and ghost number 3 in the anti-holomorphic sector. Okay, which means that you can add B, C in pairs, but you cannot just add one more C, okay, or just one more B, okay, because that will violate the ghost number conservation. Okay, are there questions? Okay, so this normalization is a matter of convention that depends on how you normalize the vacuum. And now let me say how we are going to normalize the vacuum. So we define first, I think this we had already done last time, maybe, but let me do it again. This is e to the I k dot x of 0 on the vacuum. Okay. And then we normalize as follows: the matrix element of C minus 1, C bar minus 1, C0, C bar 0, C1, C bar 1 on K prime. This we take to be 2 pi to the 26 delta 26 K plus K prime. Okay. And once you have defined this normalization condition, then all other correlation functions are determined. Okay, basically by analyticity and operator expansion and so on. Okay. So one of the basic correlation function, let me write down. Okay, so this, using this, one can show that if we take something like this, so let me order them so that the signs are correct. Okay, so product of the C's and then product of the to the IKI dot X at Zi prime, Zi double prime bar. Okay. So this one is given by the following expression. So this you can recognize is coming from the C's. Okay, so this is and 2 pi to the 26. Okay, this is a momentum conserving delta function. And then starting with this, and then you can insert arbitrary C's and B's, their derivatives, partial x, bar x, and so on. Right, all of those we can figure out just by analyticity and the operator expansion. Okay, so in this this particular CFT that we are dealing with, okay, all correlation functions can be explicitly computed, and it's not surprising because after all we are dealing with fields, right? If you remember the original action that we started with, okay, X appeared quadratically as well as BC appeared in the quadratic pair, right? So it's not surprising that we can figure out all the correlation functions. Okay, the only subtle part is this ghost number conservation, that we need 3 C's and 3 C bars to get a non-zero correlation function. Okay, now before I proceed, I have to give one final definition, and that is the BRST current and BRST charge. At least final definition for now is a BRST current and charge. So the BRST, the holomorphic part of the BRST current, JB of Z, is defined as C times Tx. Okay, so Tx is the component of the energy momentum tensor that came from X. So this is minus del X mu eta mu plus BC partial C, and then JB bar of Z bar is C bar T bar X plus B bar. Okay, so these are definitions of BRST current, and with this you can define now the BRST charge QB as integral mod Z equal to constant JB of Z dz plus integral mod Z equal to constant JB bar of Z bar dz bar. And these contour integrals are normalized. These are normalized so that integral dz by z equal to 1 and integral dz bar by z bar is 1. Okay, which means that you have included appropriate 1 over 2 pi I and minus 1 over 2 pi I factors in the definitions of these contour integrals. Okay, so that's the definition of QB. Okay, and here is an exercise which is a little complicated, but it's certainly doable. Okay, that one can show that QB is nilpotent for D equal to 26. Okay, so that's another place where the D equal to 26 makes its appearance. Okay, of course, it's not unrelated. It's related to the fact that the energy momentum tensor, total energy momentum tensor, becomes primary precisely n equal to 26. Okay, so now we are going back to string theory. And string theory is not quite conformal field theory. Okay, although conformal field theory plays a crucial role in formulation of string theory. Okay, because not all states in the CFT are physical states of the string. Okay. So physical states are a subset of states of in the CFT. Okay, and I'll not try to describe what particular subset of states you should pick for physical states. So given a state V in the CFT, it is a physical state of the string if the following conditions hold. If B0 minus on V equal to 0, L0 minus on V equal to 0, QB on V equal to 0, and V has a Gauss number 1 or 2. B0 minus, we have to define what these are. So B0 plus minus is defined as B0 plus minus B0 bar, and L0 plus minus is defined as L0 plus minus L0 bar. So this is sometimes called a level matching condition. Okay, so this condition that you have to impose is essentially due to the fact that the gauge, we gauge fixed, okay, to go to the conformal gauge, but that doesn't fix the gauge completely because a translation along sigma remains symmetric, and you have to impose the condition that all states are invariant under translation under sigma of sigma. Okay, and that's this condition, L0 minus 1 V equal to 0. And this is a condition that you have to impose together with this. Okay, I'll not give very much details of this, but this basically follows from the VRST procedure and this condition over here. Okay. But operationally, it should be clear what it means. Take a state V, okay, check if all these conditions are satisfied. If all these conditions are satisfied, then V is a physical state of the string. But there is something more, okay, and that's an equivalence relation. So if V and V are physical, V and V tilde are physical states, they are equivalent, okay, in the sense that they describe the same physical state. Okay, or if you are thinking in the language of quantum field theory, you will say they are gauge equivalent. They are equivalent if V minus, if there is a state W such that V tilde minus V is QB on W, but W has to satisfy the same conditions, that the level matching condition. Okay, so if this if W satisfies these conditions, and if V tilde minus V happens to be of the form QBW, okay, then we will declare V tilde and V to be equivalent. And we'll encounter examples later where it will become clearer what this equivalence really means. Are there questions? Okay, now let me state a result. Okay, it's a bit complicated to prove. Okay, in fact, this was proven in the early days of string theory, but with some effort. But it's simple to state that for non-zero k, okay, if you're looking at states with non-zero momentum, in the zero momentum sector, there are additional subtleties. We can take where Y is a dimension 1, 1 primary in the matter sector. Okay, so matter sector means it's built from X. Okay, it can be to the I k dot X, partial bar X, and so on, but no ghosts. So what does it mean? This means that imagine that you have found a BRST invariant state, okay, which is physical. Then by adding appropriate QBW, okay, you can always find a W, so that by adding appropriate QBW, okay, you can bring it into this form. Right? That's what it means, that by saying that we can take the represented states to be of this form. But I should have also said that this equivalence relation, or equivalence, is sometimes called a BRST cohomology. Okay, if you are familiar with the language of differential geometry, okay, then you can think of QB as the D operator, okay, which squares to 0. Okay, and you define the closed forms as ones which are inherited by D, and exact forms are the ones which are of the form D on something. Okay, so that's the cohomology. So you define the equivalent classes of differential forms as the set of closed forms modulo exact forms. Okay, and this is on a very similar scale. Okay, that, and this of course is all consistent only because QB is nilpotent, right? Because if V tilde and V are both inherited by QB, okay, then clearly this has to be inherited by QB, and that's possible because QB square is 0. Okay, so nilpotence of QB is essential for even defining the BRST cohomology. So in short, one says that the physical states of the string theory are in one-to-one correspondence with the BRST cohomology classes. Okay, and BRST cohomology class is precisely this, that is the set of QB invariant states, okay, up to equivalence, okay, that if two states differ by QB on something, then they're declared to be equivalent. Okay, so now I'll describe some examples of physical states. So the first example that I'll be considering is C, okay, of Y. Okay, so I just have to specify Y. Y as e to the I k dot x. Okay, it's a primary. Okay, and it has dimension k square by 4, k square by 4. Okay. So we need k k square equal to 4. Okay, for it to be to describe a physical state, because in a dimension 1 primary. Okay. Now I should have said this before, but let me say it now. Our convention for eta mu nu is what is called the mostly plus, which is -1 for the time and then +1 for the rest. Okay. So in this convention, this implies that minus k0 square plus k vector square is 4, okay, or k0 square is k vector square minus 4. Okay. Now, if you compare this with the usual mass cell formula, compare with k0 square equal to k square plus m square. Okay, here m is like the mass. Okay. So you see by comparing this that we have a state with m square equal to -4, okay, which is called a tachyon. So clearly this is not something physical, and because of this m square equal to -4, okay, in fact because of this the bosonic string theory is not fully consistent. Not fully consistent. Now this of course is a serious problem for bosonic string theory, but this will be rectified in the more sophisticated version of string theory, namely heterotic and superstring theories. Okay, so for now we'll proceed with the bosonic string theory because it's a good toy model. But we have to keep in mind that this theory is not fully consistent. Okay, keeping this in mind, let's go to second example. Of a physical state. Okay. Here we will take y as zeta mu nu. And we impose the condition that we have k square equal to 0, k mu zeta mu nu equal to 0, and k nu zeta mu nu equal to 0. Okay. So here this condition is coming from the dimension requirement, dimension 1, 1. Okay, because what happens is that when k square is 0, this has dimension 0, and these provide dimension 1, 0. This is 0, 1, and this is 1, 0. So that's how you get dimension 1, 1. These conditions are coming from the demand that they are primaries. Okay, so these are given as an exercise to check that once you demand y to be a primary operator, you must have these conditions. Okay, otherwise there are addition. When you take the operator expansion of t with y, you get additional terms, okay, which are not of the kind that a primary should have. Okay, so zeta mu nu here has no symmetry. Okay, but now I'm going to decompose this into symmetric, antisymmetric, and traceless part. So the symmetric part of zeta mu nu, this describes the graviton. Okay, and this is real physical graviton. Okay, not the worldsheet gravity, but gravity in space time. Okay, because mu and nu run from 0 to d, 0 to d minus 1. So to symmetric and traceless. Okay, we'll see the signal of general coordinate invariance in a few minutes. Okay, right now it's just the symmetric rank to tensor, and hence we identify this with the graviton, and it's massless, of course, because k square is 0. Then the trace of zeta mu nu, this describes a massless scalar which you also refer to often as a dilaton. And then the antisymmetric part, this describes a two-form field, B mu nu. Okay, so bosonic string theory has all these fields, all these massless fields in its spectrum. Now we are going to study the effect of the equivalence relations. Okay, because not all zeta mu nus are necessarily independent states, because you have to check what the equivalence relations are. So equivalence relations. So for this, let's take W to be, see, because of the state operator correspondence, I can either write in terms of state or operator. Here I'm writing in terms of operator. Okay, and you have to get used to this fact that we interchange state and operator freely. Okay, and we take k square equal to 0 as before, and then we also impose k nu equal to 0 and k mu. Okay, otherwise these are just constant vectors. Now, again, I'll leave it as an exercise. Okay, it's just some algebra to show that QB on W is proportional to I times K nu Okay, so this symbol means that you take the whole operator, okay, evaluate it as 0. So the 0 refers also to C and C bar and these. Okay, everything, the whole operator is set equal to 0 and acting on the vacuum. Okay, so if you are, so this is the, here I have written it as a state. Okay, if you are expressing this as an operator, you don't have to write this part. Okay, so this is a possible shift. So two states that differ by this, okay, are taken to be equivalent because it's of the form QB times W, QB on W. Okay. And this essentially translates to an equivalence relation on zeta. Because you see zeta came exactly in this combination. Okay, zeta mu nu multiplied exactly this operator. Okay, and C bar of course is there because that's part of V, right? We have taken, let's see where it is. Yeah, you see, V already has a C bar. Okay, that's the full operator. So the equivalence relation in this case takes the form of delta zeta mu nu. Okay, so that means under this kind of change of zeta, the physical state doesn't change. So that will be proportional to I k nu xi mu minus k mu xi bar mu. Sorry, k nu. I think did I do it correctly? Yeah, I think this is correct. Okay, so this one has both symmetric and antisymmetric cases. So if we take zeta bar mu equal to zeta mu, sorry, xi bar mu equal to xi mu, then you get a symmetric equal to minus xi mu. Okay, then you get a symmetric combination over here. Okay, so this gives the gauge transformation of graviton. Okay, so here delta zeta mu nu is proportional to I k nu xi mu plus k mu xi nu. Okay, and this is precisely linearized general coordinate transformation. Okay, and the other one where you take xi bar mu equal to xi mu, this gives the gauge transformation of B mu nu. Okay. Okay, this is the momentum space. In position space, it just becomes the derivative. K mu becomes the derivative of psi. Are there questions? Okay. So this is essentially linearized general coordinate transformation. This shows a linearized Now, to establish full general coordinate invariance, to establish full nonlinear invariance, we need to show that the unphysical, these pure gauge states okay, so these pure gauge states is analogous in analogy with gauge theory. So pure gauge states are precisely those for a zeta mu is proportional to this. So you have to show that these pure gauge states decouple from the S matrix. Okay. So once you have shown that, okay, then there is a general result of Weinberg, okay, which says that you basically get a general coordinate invariant theory of gravity in a low energy limit. Okay, so this is a property of the S matrix that you have to prove, that these pure gauge states decouple from the S matrix.
Sorry, which ones are the pure gauge states?
These, if you take the zeta mu nu to be proportional to k nu xi nu plus k mu xi nu, for example. See here, what I'm saying is that if you change zeta mu nu by this, then this is this generates an equivalent state, right? So which means that if when you calculate the S matrix, whether you use zeta mu nu or zeta mu nu plus something proportional to k nu xi mu plus k mu xi nu, you should get the same result. So for this reason, when zeta mu nu is taken to be this itself, okay, the result should vanish. And those are called the pure gauge states.
Thank you.
Okay. So in electrodynamics, this will be the analog of the photon whose polarization is proportional to k. Okay, and we know that those are supposed to decouple in the from the S matrix. It's the exact analog of that in gravity. Any other question? Okay, so this of course requires that you have to first define what S matrix, what string S matrix is, and these will be discussed eventually. Okay, how we actually prove this decoupling. But let me just say at this stage that besides these states, we also have infinite tower of massive states. Okay, so those are obtained by basically building up higher and higher weight states. You see that typically it has the structure, all these states have the following structure, that you have some operator over here multiplied by e to the I k dot x. And one feature is that the k has to be adjusted so that the dimensions match up correctly. Okay. So these infinite tower of massive states basically come by using higher derivative terms here. Okay, say multiple derivatives of x or products of many del x's, partial x's. Okay. And then of course you have to adjust the coefficients appropriately so that these are primaries. Okay. But by building this tower, okay, and making it into a primary, okay, the corresponding k square, okay, will have to be adjusted so that the dimension adds up to 1, 1. Okay. And that you can easily convince yourself that produces massive states. Okay, that's like the lowest state gave the tachyon, okay, m square negative. These gave m square 0. Okay, and once you include higher oscillators or higher powers of these operators, okay, you get massive states in the spectrum. Okay. But the mass scale of these is set by the string scale. Okay. Which of course we are taking to be 1. Okay, but if you want to put back the dimensions, okay, it's basically goes as 1 over square root of alpha prime. Okay, this is in h bar equal to 1, c equal to 1 unit. Okay, but if you don't set alpha prime equal to 1. Okay. And the idea is that these can be made unobservable today. By taking the string scale to be sufficiently large. Okay, and typically one takes the string scale to be of the order of a Planck scale. Okay. In which case, of course, these are clearly not observable today. Okay, because Planck scale is like 10 to the 19 GeV. Okay, whereas today we can only see particles of masses up to, say, at most a TeV. Okay, which is 10 to the 3 GeV. Okay, so we are not going to discuss this any further. Okay, this is of course a good topic of string phenomenology. Okay, But we now go back to correlation functions. Okay. So the goal is to compute S matrix. And so for this, we need to return to CFT correlators. Now, if you recall, we had introduced this notation for the CFT correlator. Now we are going to introduce some new concepts, okay, or new definitions. Okay, first, punctures. Okay. These are just new names for the locations of the vertex operators. Okay, these are the vertex operators. So the punctures in this case are at z equal to z1, z2 to zn, right? So you'll say that this is the here you have a sphere with n punctures. Now we introduce something new. Around each puncture, we introduce a local complex coordinate system which I'll call Wi. Okay. And we did this separately for each puncture. Okay. I equal to 1 to n. So the convention that I'll be using is that the ith puncture is located at W equal to 0. Sorry, Wi equal to 0. Okay. And in general, there is a functional relationship of the form z equal to fi wi for every I. Okay. So what am I doing? Okay, what I'm doing is the following. So you have the complex plane which has this global coordinate z that we use to define it. Okay. Now you say that near each puncture, okay, I introduce some arbitrary coordinate system wi, okay, which locally is holomorphically related to z. Okay. But otherwise, we don't put any additional restriction on fi. Okay. And the fact that the puncture is located at w equal to 0 means that zi, okay, which is the location of the ith puncture in the z plane, this must be equal to fi of 0. Okay. So, for example, you could take fi of wi to be wi plus zi. Okay, that's a simple case. Okay, that's a possible choice. Easy. This is an example. Because at wi equal to 0 maps to zi. But you could also check or because this also has the property that wi equal to 0 maps to zi. Okay. And the only condition that we impose is that around that point wi equal to 0, the map between z and w should be 1 to 1. Okay, but of course it need not be 1 to 1 everywhere, because this, for example, you can clearly see that if Z is Wi plus Zi plus Wi squared, then when you try to solve for Wi in terms of Z, okay, there are branch points, right? It's not, there's a unique solution to this equal to Z equation. Okay. But all you need is that near Wi equal to 0, this function is 1-to-1 and analytic. Now, what's the role of this Wi's? Okay. So we'll be considered a correlation function where Vi is inserted at the ith puncture using Wi coordinate system. Okay. So when you insert V, you just insert V of Wi. Okay. But this becomes Fi dot Vi of 0 in the Z coordinate system. Okay, this in fact is a definition of what we mean by Fi dot Vi. Okay. Because Z and Wi are related by this Z equal to Fi of Wi. Okay. So if you insert something in the Wi coordinate system, say at Wi equal to 0, then the Z coordinate system, that operator, will have the form Fi dot Vi of 0. Okay. So we'll consider the correlation function. Correlation functions of the form okay. So let me emphasize again, this basically means, okay, so this is in the Z coordinate I've written, but this basically means that Vi is inserted in the Wi coordinate system. Okay, and this Fi dot Vi is needed because you have to convert this from Wi to the same Vi written in the Wi coordinate system becomes Fi dot Vi of 0 in the Z coordinate system. Okay, and this is the coordinate system in which we have written the correlation function. Okay. Now, in this form, okay, SL2C invariance has a simple interpretation. Okay, so SL2C invariance tells us that this correlation function can be also written as product where H is an SL2C transformation. And this, in fact, can be written as, if we call this Fi hat dot Vi of 0, okay, where these are new maps. Fi hat of Z is just H of Fi of Z. Okay, because this notation basically means that we first transform Vi using the Fi coordinate system and then using H, right? But that's the same as transforming by this function H of Fi of Z. Okay. So in this, from this perspective, the SL2C invariance, okay, basically says that if you keep the local coordinates fixed, okay, but change the coordinate Z by an SL2C transformation to Az plus B over Cz plus D, okay, then effectively these functions Fi change, not because the local coordinates have changed, but the global coordinate you have made an SL2C transformation. Okay, and that's an invariance of this correlation function. So whether you use the FIs or FI hats, you should get the same answer. Okay, so these are just some definitions that will be useful in what we are going to do next. Are there questions? Okay, now one more set of notations. So we are going to introduce a set of basis states. In fact, not one set of basis states, but two sets of basis states. One set I'll call phi r, and the other set I'll call phi rc in the CFT. Okay, so this is in the full CFT, not in this physical subspace. And we'll choose them such that, so each of them are complete set of basis states. Okay. But we'll choose them such that the following condition holds. Okay. I mean, it would have been inconvenient to use, for example, phi r phi s equal to delta rs, okay, because this inner product, as you know, the total host number has to be 6, right? So if phi s has host number 1, then phi rc must have host number 5. Okay, so the pairing is between different host numbers. Okay, that's why we need this different set of basis states. Okay, we need two different sets of basis states. Okay. Now this implies also the following condition: phi s phi rc is minus 1 to the phi s times delta rs. Okay. So what is minus 1 to the phi s? Okay. So this one basically is 1 . This one is 1 if phi s is Grassmann even. That means it has even ghost number, because the Grassmann odd nature comes only from the ghosts. And it's minus 1 if phi s is Grassmann odd. Which means odd host number. Okay, that's what I would mean by saying this minus 1 to the phi s symbol. Okay. And the way to prove this is simple, because you see, this is what this is. I can write it as the vacuum expectation value of I. Well, maybe I don't have to write on vacuum expectation value. I write this is a correlation function. Okay. Now we can make an SL2C transformation by I. Okay, I is minus 1 over Z, right? So let me remind you. I of Z is minus 1 over Z. Okay. So I can make an SL2C transformation by I. So this becomes phi rc0, I dot phi s of 0. Okay. And all you have to do now is that you have to exchange that position, okay, inside. Inside the time ordering, of course, exchanging position is not a problem. But if this is a Grassmann node, it become a minus sign. Okay. So this will be minus 1 to the phi s times I dot phi s of 0, phi rc of 0. Okay, and that's exactly this. Okay, that's the way this follows from this. Now, using this orthonormality, we can also write down the completeness. Let me write this. So this is an exercise. Sum over R, phi rc is identity, and sum over R phi R C phi R minus 1 to the phi R is identity. Okay, these are easily proven by taking the applying this on some base state phi s and showing that you get phi s on both sides. Okay, so now I'm going to, let me go to the next slide, because this is going to be a little complicated, so I have to proceed somewhat slowly. So you are going to consider a correlation function of the following form. And we assume that mod Fi0 is larger than mod Gj0 for all PRIJ. Okay. Then we can write this as a radial order product. Okay. And in the radial order product, this will come before this, okay, because of this condition. So with this, I can now write A as follows. Now I'm going to insert a complete set of base states. I have to write it in the next slide line, but it's okay. I hope it's clear what I have done. I wrote it as a vacuum expectation value with the radial order product of these first, then the radial order product of these. Okay. And then inside this, I inserted two identity operators. So this is identity. Okay. And then this phi sc, phi s minus 1 to the ns, this is again another identity. Okay. Unfortunately, it has gone to the next line. So let me just draw a continuity over here. So I inserted two identity operators and then wrote the rest. Okay, let's now try to manipulate this part. Okay, so what I'm going to do now is to just take this part and manipulate this. Eventually, we'll put them back together. Okay. And the idea is that I want to write this in the same way that we have written the top one. So this one I can write first of all as I.
Sorry, Ashok, you should also add the summation over R and S, I guess.
Yes, yes, okay. Sorry, I should have written this. Maybe I should say I am not writing it because I'm using the Einstein summation convention. Sum over R and S implied. Okay, so when I write phi R, C, it's understood that I'm summing over R. Similarly, phi S, C, phi S, it's understood that I'm summing over S. Okay, I'm just not writing the sum explicitly. Thank you. Any other question? Okay, so let me write this as I dot phi s of 0 minus 1 to the ns, and then the radial ordering well, actually I don't have to write it. Let me remove this radial ordering. Okay, and let me explain what I have done. Okay. So this phi s I can write I dot phi s 0. Okay, at this stage I still have to have this radial ordering. Okay. But now you see that I of 0 is infinity, right? So this is already in the leftmost position. Okay, so if it is inside the radial ordering, okay, it would still be at the leftmost position. So what I can do is that I can put the radial ordering in front of the whole product, and then just remove the radial ordering and written this as a correlation function. Okay, I hope it's clear. Okay. So this I first wrote as a vacuum times I dot phi s of 0. Okay, and you still have this. Okay. And then I just removed the radial ordering and wrote it as a single correlation function, because in any case I dot phi s of 0 has to be on the extreme left inside the radial ordering. Now I'm going to use an Slqc transformation. So this one I'm now going to make an Slqc by fq dot I. Okay, I have already introduced earlier. So what is fq? Okay. So fq of z is just scaling qz. Okay, so that's also an Slqc transformation. So fq dot I is an Slqc transformation, so I can make that transformation. So then I can write this. I square is minus 1. So fq dot phi s of 0 minus 1 to the ns. And then here we have fq dot I dot gi dot v tilde I of 0 product I equal to 1 to m. Okay, I hope this is clear. So this is not ns, this is phi s. Okay, now fq dot phi s, okay, the scaling, this is, I can write as q to the hs, q bar to the hs bar, phi s of 0. Okay, now I'm going to take this phi s of 0, okay, and put it on the extreme right. Okay. Inside radial ordering, of course, it doesn't matter where you write it, provided you pick up the appropriate minus signs because of the Grassmann odd nature. And you see that if phi s is Grassmann odd, okay, that means if it has an odd Gauss number, then the rest must also be Grassmann odd, because the total Gauss number has to be 6. So if phi s is odd, then the rest is odd. So while pulling it on this side, you will pick up a minus sign. That will cancel the minus 1 to the phi s from here. If phi s is even, then of course there is no sign involved. Okay. So, and then minus 1 to the phi s is 1. Okay, so basically we can pull this phi s on the right, okay, at the cost of removing this minus 1 to the phi s. So at the end of it, I can write this as product I equal to 1 to m. Okay. Let me write this as, I think I have called this f tilde I dot v tilde I 0 times phi s of 0. And then you have this q to the hs, q bar to the hs bar. And what is f tilde I? Okay, it should be clear from the definition. F tilde I is just fq dot I dot gi. Okay, so this is some simple manipulation involving Slqc transformation to bring this into this form. So I'm going to write down in the next slide, okay, the relation that we have obtained so far. So what we have seen is that we started with product over I, fi dot vi of 0, product over j, I equal to 1 to n, j equal to 1 to m, gj dot v tilde j of 0. This I now rewrote as product over I equal to 1 to n, fi dot vi 0, phi r of 0. Then I have a factor of phi r c, phi s c, q to the hs, q bar to the hs bar. And then product j equal to 1 to m, f tilde j dot v tilde j of 0, phi s of 0. So this manipulation that I did was basically to make it look symmetric between the top one and the between this one and this one. Okay, that's the only reason. Otherwise, I mean, I haven't really done much with this. So what this is saying is that if you have an n plus m point correlation function, it's telling us how to write this in terms of a lower point correlation functions. But I'm now going to give a geometric interpretation of this equation, okay, which will be very useful, and this geometric interpretation is what we're going to generalize. So this is a correlation function on a sphere. Okay, so this I'm going to call a sphere S. Okay? And this is a correlation function on a sphere. Okay, I'm going to call it the sphere S prime. Okay. So what you have is two spheres, S and S prime. Okay. I introduce complex coordinate Z on this and complex coordinate Z prime on this. Okay. Here I have a set of punctures. Here I have a set of punctures. Okay. So on this side, I have the relationship Z equal to fi of wi. Okay, where wi are the local coordinates around these punctures. On this side, I have the relation Z prime. You'll see here you have the local coordinates f tilde j. So f tilde j of w prime j. Okay. These are the local coordinates around these punctures. And now you see that this has one extra puncture, okay, phi r of 0. So that's, let's call that the extra puncture. So this is the n plus 1th puncture on this side. N plus 1th puncture. On this side also there is one extra puncture, m plus 1th puncture. Okay. Here the local coordinates are just z and w, z and z prime. Okay, because there's no transformation involved here. Now let's consider a small circle around this, and the small circle around this. Okay. This circle is defined by w n plus 1 equal to mod q to the half. This circle is defined by w prime m plus 1 equal to mod q to the power half. Okay. And then identify this by using the relation wn plus 1 w prime m plus 1 equal to minus q. Now, why am I doing this? The purpose of doing this is to show that once you make this identification, you see, once you make this identification, then these two spheres that you have get glued together into a single sphere. What I'm going to argue now is that the glued sphere that you get here is precisely the left hand side. That's the glued sphere. So let's see how we go about saying this. So on the glued sphere, we can use either the z coordinate system or the z prime coordinate system. As so what is the relationship between z and z prime? Okay, we can read out from here. So z, we have z on this as wn plus 1, wn plus 1. So which is minus q over w prime m plus 1, okay, because you have identified by this relation. Okay. But w prime m plus 1, okay, around this puncture, z prime is w prime m plus 1. You see the local coordinate here is just identity, right? So z prime is the local coordinate. So w prime m plus 1 is nothing but z prime. Okay. So this is minus q over z prime. So now if we look at the punctures over here, okay, so let's take the jth puncture over here. Okay. So let's take jth puncture. Okay. So here you have the relation that z equal to minus q over z prime. But what is z prime near the jth puncture? Okay. Z prime near the jth puncture is f tilde j of w prime j. But minus q over f tilde j of w prime j, what is it? Let's go back. The definition of f tilde j. You see, f tilde j is here, right? This is, let's complete this. This is minus q over gi. Okay. So minus q over f tilde I is nothing but gi. So this is precisely gj of w prime j. Okay. So relationship between z and w prime j is just z equal to gg of w prime j. That's exactly the left hand side. This is going to be very important in the rest of the lecture, so it should be clear what we are doing here. Okay. Are there questions, or is anything not clear in this manipulation? Okay. So let me repeat again what I'm going to say, what I'm saying here, that we have the left hand side, we have the right hand side. So let's look at the right hand side, an expression like this. Okay. What we are saying is that whenever you have an expression like this, okay, this can be reinterpreted, okay, as the correlation function on a new surface, okay, where you have glued these two individual surfaces together, okay, by this precise relation. Okay, the gluing relation takes the form wn plus 1 w prime m plus 1 equal to minus q. Okay, q is the same parameter that appears here. Okay, so whenever you have a correlation function of this kind, you can reinterpret this as a new correlation function that appears on the left hand side. If this is clear, if there are no questions, I'm going to write down now a generalization of this relation. Okay, so more general result. Okay. So the generalization is basically at this stage, okay, will be to relax this constraint that these are identity, okay, that the local coordinates here are identities. So we'll now describe the case what happens when the local coordinates here are not identity. That the relationship, the if n plus 1, for example, here was just a simple identity map, that's not going to be the case anymore. So if we consider okay, all through the sum over R and S is implied. This is equal to a correlation function on a new surface, which is of the following form. So what is the difference? Okay, so first let's see how this new surface is constructed. Okay, so this one is obtained exactly in the same way. Obtained by showing the two spheres, two original spheres, by Wn plus 1, W prime m plus 1 equal to minus q. So the only new ingredient here is that because the relationship between Z and Wn plus 1, okay, is not simple, is not SL2C. Okay, the map between Z and Wn plus 1 is not invertible. Okay, so as a result, what happens is the Z coordinate system, which is valid here, okay, you cannot really continue it all the way to the other side. Okay, unlike what we did earlier, right? We found out the relationship between Z and Z prime, a simple SL2C relation, and then we continued it to the entire plane. Okay, that cannot be done. Okay, and as a result, neither Z nor Z prime is a good global coordinate on the resulting sphere. Okay, so we need a new coordinate. So the global coordinate on the resulting sphere is some Z double prime, which you can construct. There are well-defined algorithms to construct this, but it's not Z prime, Z or Z prime. Okay, and so the idea is that once you have constructed a new coordinate Z double prime, okay, we have to find the relationship between Z double prime and the local coordinates here. Okay, so Z double prime will be now given by f hat I of Wi. This is near the ith puncture on the original sphere. Okay, and similarly Z double prime will be given by f tilde hat j of W prime j. Okay, so you can figure out what is f hat and f tilde hat are once you have found out what the Z double prime is. Okay, but in general, finding Z double prime is not very simple, right? It's algorithmic. It's possible to find Z double prime, but it's not just simple solving algebraic equations, right? Unlike what we did in the previous case. Okay, so in the special case, we had these f n plus 1 and f tilde m plus 1 and SL2C transformation. Okay. You can extend either the z coordinate or the z prime coordinate through the entire plane. Okay. But otherwise, constructing the z double prime will involve some work. Okay, but this is a general relation that we can always use. Are there questions? Okay, now let me then.
No, Ashok, there is a question. Sorry, just
Yes.
in the
Go ahead, please.
Can we
Yeah.
use the Slqc group construction of that glued surface to write the coordinate z prime prime?
Yes, we could. Yeah,
Okay.
we can certainly do this. Yeah.
And is that obvious then how z prime prime will be written in terms of that the Slqc group, or is it still hard to find it?
Yeah. So typically, you have to solve a differential equation to do this. Right. In simple cases, you can find it. Okay. I think for the Slqc group, it's still SL2C. You are identifying by the SL2C transformation, right? So in that case, I think you can still do it in a closed form, but otherwise it will involve solving a differential equation.
Okay, thanks, Ashok.
Okay, now let me just say one last thing, and this I'll elaborate on next time. Okay, I mean why I'm getting that there. Okay, because you have of course learned how to calculate sphere correlation functions anyway, so we don't need to use all this machinery to compute higher point functions in terms of lower point functions. Okay, but we are going to generalize. Okay, and that's as follows. Suppose you had this. Okay. So the only difference between this and the previous cases is that here, instead of picking two punctures from two different spheres, I have picked two punctures from the same sphere. Okay. But the philosophy is exactly the same. Okay. So what this tells us that you have to now take the sphere and glue again Wn plus 1, Wn plus 2. So this corresponds to this gluing. Okay. And if you draw the picture, it will become clear what is happening. So you have a set of punctures over here. Okay. And now you have these two n plus 1th puncture and nth puncture. Okay. We are identifying this by this relation Wn plus 1, Wn plus 2 equal to minus q. Okay, this is Wn plus 1 equal to mod q to the half, and this is the mod Wn plus 2 equal to mod q to the half. Okay. And you can easily convince yourself that if you do make this identification, okay, what we get is a torus. N punctures on a torus. Okay. So then what this is telling us, okay, is that you can calculate the n point correlation function on the torus, okay, in terms of n plus 2 point correlation function on the sphere. Okay. And this in fact is quite general. You can build the correlation. Did I get muted for some reason?
Okay, it was my fault. I'm sorry. Yes, but
Yeah.
please repeat your last sentence.
Yeah. Okay. So the point here is the following: that once you have made this identification, right, what you produce is a torus. Okay. Because you can see that once you identify this with this, okay, you have basically joined a handle on the sphere. Okay. So what you get is n punctures on a torus. So yeah, on this side you have the endpoint correlation function on a torus. Okay. And what this relation is telling us that the endpoint correlation function on the torus can be constructed from an n plus 2 point correlation function on the sphere. Okay. And this procedure can be generalized to any Riemann surface. Okay, by keeping on gluing, okay, keeping on showing punctures. Say, for example, if you now show this puncture with this puncture, okay, by again making some identification, okay, among these, okay, then you get a genus 2 surface. Okay, so all correlation functions and all Riemann surfaces, okay, in principle can be constructed in terms of correlation functions on the sphere. Okay, so that's the main lesson of this exercise. So I think my time is up, so I'm going to stop here and we'll continue tomorrow more on this theme.
Okay, so thanks a lot, Ashoke.